Really great to be here at the, oops, yes, I got it, at the Q flag seminar. I haven't come as much as I would like to, but it's really great to speak here. So we are, all the talks I've been giving lately, because we're in the middle of a pandemic, there's a lot of mathematicians who died in the pandemic, and certain who, were really influential in Brauer groups and linear algebraic group communities. So, I mean, two notable people that I just point out is Ray Hubler, who died very, very early in the pandemic, and Humphreys as well. I knew Ray quite well. I was a colleague of his at the, when I was at the Courant Institute, and he was a good friend of mine. All right, so here's the problem. Here's the statement of the problem, and I'm going to spend, the first probably half of the talk motivating why you should be interested in it. But here's the statement. So you have just an arbitrary field, and then you just ask, is every central simple algebra A split by a genus 1 curve over K? So what I mean by that is, split by the function field of a genus 1 curve. And by genus 1 curve, I mean a smooth, proper, geometrically connected curve of genus 1. So if it splits a central simple algebra, necessarily it has no rational points, and we'll get into that. But that's the question. So, okay, we talk about, if we have a central simple algebra, we talk about splitting fields as fields where if we base extend, we just get the matrix algebra. That's the standard definition. So this field could be finite, could be infinite degree. And we could talk about splitting varieties, it's say a variety, say geometrically integral or something over our field, so that its function field is a splitting field for the algebra. So generally, I mean, historically, everybody cares about splitting fields that are of finite degree. So, and this is kind of the definition of the index of an algebra, which is just the minimum or greatest common divisor of all the degrees of, finite degree splitting fields. So that's, people are really interested in the index, can bound the index, what can you say in period index? And so we care about these finite splitting fields. And so again, the index is the degree of the kind of unique division algebra that's given by Art and Wedderburn as well. All right, so we know about that. But of course, we're also interested in a positive, transcendence degree splitting fields, and kind of the most universal one is gotten by the Severi-Brauer variety. So if we have a central simple algebra of degree n over our field, then this construction, I guess going back to Châtelet, associates this Severi-Brauer variety, which is a smooth projective, K variety of dimension n-1, which is geometrically projective space of that dimension. And it has, the following universal property, which is important for studying splitting fields, which is that a field extension, finite or infinite degree over K, is a splitting field if and only if the Severi-Brauer variety has a rational point over that field. So that's somehow the idea. And of course, if you want to think geometrically, then if you have a function field of a variety that you'd like to split an algebra with, then that's equivalent to the existence of a rational map between that variety and the Severi-Brauer variety of the algebra. Okay, that's just just a translation of this into birational geometry. All right, so I'm saying everything that you know already, but let me give you a very, very explicit, easy example. So let's say we take standard quaternion algebra and characteristic not 2, AB, and its splitting field is, it's a Severi-Brauer variety. It's well known to be this projective conic given by this diagonal quadratic form. But if we give it in kind of a little bit more, I've changed variables a little bit to give it in affine coordinates like this. So in affine coordinates, we can view that conic as given by the equation y² = ax² + b. Why do I do that? Well, because now I can write down a related curve, which is a hyperelliptic curve of genus 1, which is y squared equals ax to the fourth plus b. And we have y squared equals a quartic, and we know that's a genus 1 curve, hyperelliptic curve. And of course, if you realize that you can take this curve C and map it to our conic by just squaring the x coordinate, and that shows that, this is a Severi-Brauer variety for this quaternion algebra A. This is a curve of genus 1, and this is a actual morphism. And so that genus 1 curve splits that quaternion algebra. Okay, so that's kind of a first, maybe standard example of this phenomenon of a genus 1 curve splitting an algebra. You might ask, why genus 1? Why do you care about genus 1? Okay, maybe curves you want to split algebras, but why genus 1? So if you have any smooth curve, then if it splits an algebra A, well, that's equivalent to, well, we said a rational map from the curve to the Severi-Brauer variety, but because we have a curve and x is proper, this actually closes up to a morphism. And then if we look on, on rational points over field extensions of our base field, we get maps on rational points. So any rational point over L on the curve gives a rational point on the Severi-Brauer variety. So a splitting field for the curve, or a point of the curve over a given field, gives a splitting field for the algebra. And from this, we deduce that the index, if a curve splits an algebra, then the index of the algebra divides the index of the curve. And by index of the curve, I mean, the usual index of a variety, the GCD of the degrees of field extensions over which it acquires a rational point, or the minimum degree of a zero cycle, either of those. So since we have a curve, and the index of the curve, well, it's something that divides 2g minus 2, because we always have a canonical divisor, which is some zero cycle. And it always has degree 2g minus 2. So this is, we know that any curve, smooth curve that splits an algebra, the index of that algebra divides 2g minus 2. And so you see that there's some obstruction on the genus for a curve of a given genus to split an algebra based on the index and the genus, right? But that obstruction, if g is equal to 1, that obstruction goes away and there's no obstruction. So that's why we're kind of focused on genus 1 curves, is that there's no a priori obstruction due to the genus of the curve that would, not allow that curve to, say, split a given algebra. Whereas if you had a higher genus curve, like a curve of degree 3, I mean, you couldn't split certain algebras of certain index just because of this obstruction. So you see where the genus equals 1 condition kind of comes in very naturally here. All right, so what's the history of this question? Is every central simple algebra split by a genus 1 curve? Well, I guess really, Saltman, the first time I ever heard about it was at a conference in Emory in 2011, and Saltman asked this question at the open problem session in the middle of the conference with some notes written up after that. So that's the first time I ever heard about the question. But Saltman says he's, been trying to talk about it for a long time. Before that, he says actually somehow it's motivated by work that Artin did. Pete Clark also had been asking this question. He had this question posted on a website of open problems that used to be on his website, but he's since taken that page down, so you can't really see. But I have an old copy of that website of Pete Clark. So this question has kind of been kicking around, but let me just tell you about some of the history. So some work of Roquette and Lichtenbaum shows, this is not what they intended to prove, but you can extract this from their work, that yes, if you have a p-adic field, then every central simple algebra is split by some genus 1 curve. In fact, if you take an algebra of index D, then if you take any genus 1 curve of index D, then it will also split that algebra. So that's a nice feature. If you go back to work of Artin, kind of in one of his foundational works on this, geometry of Severi Brauer varieties, and there's a thesis of Sweat's that the answer is yes if the degree is, at most 3. So gave kind of, just like I gave above, it just gave kind of a geometric construction for how you might split an algebra based with a genus 1 curve. There's another way to study the problem, right? You could fix a genus 1 curve or fix a variety and ask which Brauer classes from the base field are split by that particular variety. That's the so-called relative Brauer group. And so this is somehow related, right? I mean, we're asking, with this question, we're asking basically, is the whole Brauer group filled up by the union of relative Brauer groups of genus 1 curves, right? But you could take a genus curve one at a time and study its relative Brauer group. And Cipriani and Danny Krashen and Lieblich, at various points studied, this relative Brauer groups of genus 1 curves. Finally, this question was really, addressed in a paper, stated, and some results proved by Wei Ho and De Young, that yes, it's true if the degree is at most 5. And then, back in 2015, I actually spoke in Banff about the case of degree 6. I gave, the talk is online. You can see my, idea for proof in that case. I meant to refine it, make it better with Marcello Bernardara. We've been trying to make it really nice, but there's nothing published on it yet. But I think yes, for the degree 6 case should also work. But I'll just say notably, open is over Q. I mean, still this question is completely open over Q. And it's also just open in general for cyclic algebras. Is every cyclic algebra split by a genus 1 curve? Of course, if you could answer that, then you could answer it for Q, because every algebra is cyclic over this type of field. But just to show you the paucity of what we know about this problem, here are some notable open cases. You can, feel free to interrupt me anytime or put questions in the chat. I see the chat open. So here's the theorem I wanted to talk about today. So this is joint work with Ben Antieau that came out last year, I guess. That had been the object of many years of work and talking with each other about it. But we proved that every algebra of degree 7 over a global field is split by a genus 1 curve. And we also handle various other cases, like degree 10 algebras, 8, 9, and 12 under various restrictions on the global field. And so, but I think for us, we were most proud of dealing with this degree 7 case, because that's kind of the next prime of interest. And one remark that I'll make here for those kind of arithmetic, geometrically inclined, is that these numbers, so if you saw above, it's known up to degree 5, maybe degree 6, and now over global fields, degree 7, 8, 9, 10, and 12. And, that collection of numbers, n from, 1 or 2 up to 10, and then 12, that's, if you like elliptic curves, that is precisely the n for which the modular curve x1 of n has genus 0. Now you might say, where does that have anything to do with anything? But actually, this is a spoiler for the latter part of the talk, where this actually comes up in our construction. Okay, I'm going to take just a little interlude for a moment, and I want to tell you, because a lot of people here are interested in quadratic forms, so I want to popularize a kind of a version of this problem, which is, are quadratic forms split by a genus one curve? So one question you might ask, and you might ask, okay, you might ask, is a quadratic form split by a genus one curve? Now, when you start to ask that question, you have to realize that you have to ask it correctly. So first of all, it's obvious that any quadratic form can be made isotropic over a genus one curve. It's just completely obvious. You know, you take take a rank, dimension 2 subform or dimension 3 subform, take the associated conic, split it by a genus one curve that that I've just written, and then you can basically map that curve to the quadric of your, is very easy. So that's not an interesting question, becoming isotropic over a genus one curve. But becoming hyperbolic over a genus one curve, that's more interesting. And once you need to become hyperbolic over a genus one curve, you realize one obvious obstruction is the discriminant. So certainly if you have, because a genus one curve is geometrically connected, we're assuming, so you're not going to be able to split the discriminant, by going to a function field of a regular extension. So you have to assume that you have trivial discriminant if you're going to try to do this. And so that's where I think the good question is. Does every quadratic form in I2, okay, in trivial discriminant and even dimension, become hyperbolic over the function field of a genus one curve? That's I think a very interesting question. With Danny, we've been toying around with this question for a while, and it's yes, the answer is yes if you have quadratic forms in 4 and 6 variables, and you can do 8 variables if you assume that the Witt index is appropriate, or you assume that not the Witt index, but assume something about the index of the Clifford algebra. So you can do some partial things in low dimensions, just like we had partial results in for algebras. But I think open already is just quadratic forms in 8 variables, completely open. So try it. It's a really fun problem. All right. One kind of observation, I'll say. I mean, it's a theorem. It's stated a theorem in our paper, but it's really, if you read the proof, it's this kind of an observation based on what we've done that Ben and I made, is that at least one can prove that every quadratic form in I2 becomes hyperbolic over a product of genus one curves. You might say, okay, why do I care about that? Product of genus one curves, it's a particular type of a torsor for an abelian variety. And this type of question about whether a central simple algebra can be made split over a torsor for an abelian variety, general dimension abelian variety, not necessarily a torsor for an abelian variety of dimension 1, like a genus one curve, but maybe a higher dimensional torsor for an abelian variety, whether those objects can split central simple algebras. That more generalized question has a positive answer and is first proved by Weiho and Lieblich, and then Ben and I gave an alternate proof which gives something more along the line of this. So this is I'm just showing you the interaction kind of between these two problems, or the analogous things one can show. So all right, that was my little interlude about quadratic forms. So I'm just trying to popularize this problem.
So if you want to split the quadratic form, you have to split the Clifford algebra.
Even Clifford, yeah, the Clifford algebra, for example, absolutely.
So there is that connection.
Absolutely, absolutely. So that's already necessary. Absolutely. So in dimension 8, well, okay, I don't want to talk too much about quadratic forms, but yes, it is a very interesting problem and is very much related to the other problem. Okay, so where do elliptic curves come in? Where does, modular curves come in? All right, so if we have a curve of genus 1, then if we look at the Jacobian, that's the Picard, the degree 0 Picard variety of that elliptic curve, then that's actually an elliptic curve. Okay, it's a genus one curve with a rational point, with a, canonical, identity element to the group law. The curve itself, C, is just the pick one, the kind of, degree one divisors on the curve itself. And hence, via this way of looking at it, C is then an E torsor, right? And there's clearly an action of degree zero, degree zero divisors on degree one divisors just by adding divisors. And hence, the curve, the genus one curve C, becomes an element in the Galois cohomology group of the field with coefficients in the group scheme, which is the elliptic curve E, which is the Jacobian of C. And this object here is something that's often called the Weis-Chatelet group of that elliptic curve E. Now, we kind of understand a little bit about these embeddings from the Leray spectral sequence. So if you look at the Leray spectral sequence for GM and look at the the low degree, the sequence of low degree terms, you'll see this short exact sequence coming out of it. There's the Picard group of the genus one curve. There's the whole Picard scheme, okay, with all its connected components. And then there's this, boundary map, which goes to the Brauer group, ostensibly the Brauer group of the field, but it maps surjectively onto the relative Brauer group of that curve. And one way of interpreting this map here is that if elements of this Picard scheme are, I'm calling them L, but they're not literally line bundles. They're somehow, they're not literally linear systems. They're somehow Galois invariant, classes of linear systems. And so linear systems give, generally speaking, if they're globally generated, say linear systems gives maps to projective space. But these kind of Galois invariant, classes of linear systems don't give maps to projective space. It's kind of well known that these kind of objects give maps to Savary-Brauer varieties, to twists of projective space. So if you start with a geometrically globally generated one of these Galois invariant linear systems, then the associated map to a Savary-Brauer that you get that is associated under this boundary map, you just get the class of the Savary-Brauer variety, okay, the class of the algebra underlying the twist of the projective space that you had to choose. So that's a kind of a geometric manifestation of this boundary map. So what's the relationship to n-descent? So n-descent is a theory in kind of the arithmetic of elliptic curves, which is trying to say calculate the Mordell-Weil group of a given elliptic curve by viewing the Mordell-Weil group as kind of sitting inside a larger group, which is which is a Selmer group, and then trying to somehow explicitly write down elements of the Selmer group as actual genus one curves with a given projective embedding, say. So that's somehow like the idea of n-descent. But so how are we going to use it here? Well, if we start with our elliptic curve E, we have this exact sequence of group schemes in the Auel topology, or say flat topology. Let's maybe assume n is relatively prime to the characteristic. It doesn't actually matter. But this induces an exact sequence in Auel cohomology, say, like this, okay? If we look at this sequence, this is a short exact sequence that we get from the long exact sequence. And so you see that we get, the rational points modulo n, kind of inject into this larger group. And in fact, they inject into, so if inside of here, we have the so-called Tate-Shafarevich group of the elliptic curve. This is consisting of all these elements, well, at least the degree n torsion of it, all those elements that require points locally everywhere, say over a number field or over all valuations. And then in here, we have this is the so-called n-Selmer group of the elliptic curve. And so this is kind of the idea of descent, is that you view this group as somehow sitting inside of this larger group, which you could hope to say something about. But here we're not really going to need that. But what we are going to need is a technique from descent, from the theory of descent, in which they show that this group here, which the Galois cohomology over with coefficients in the n torsion group scheme of the elliptic curve, that is kind of a refinement of those genus 1 curves with period n. And the refinement is like this. So it's the data of a genus 1 curve C together with an embedding into a Severi-Brauer variety A, where the degree of that variety is equal to n. So this is pairs like this of a genus 1 curve, necessarily of period n, together with an embedding into a Severi-Brauer variety of degree n. That data, those pairs of data, is very commonly used as a representation of this set in the theory of n descent. Of course, in n descent, they're mostly interested in splitting this algebra A because they want projective representatives of their elements. So they don't really care about the algebra A. They want to actually get rid of it. But we actually care about the algebra A. So from also from this theory of n descent, there's this which is tool that was kind of brought to the forefront, studied by Cathy O'Neill and then later by P. Clark and others, which is the so-called period index obstruction map, which is a map. It's not really a linear map, but it's some kind of map from, it's not a group homomorphism, but it's some kind of almost a quadratic map from this Galois cohomology group to the n torsion of the Brauer group, which indeed all it does on this geometric interpretation is it takes a pair, an embedded genus 1 curve inside of a degree n Severi-Brauer variety, and just picks off the class of the algebra. That's the kind of geometric geometric understanding of O'Neill's so-called period index obstruction map. It has many other interpretations, but I don't really want to go into them in terms of the period index problem. So, I mean, you might then ask somehow, given a Brauer class, does there exist an elliptic curve E and a torsor for the n torsion of that elliptic curve where the obstruction map is actually equal to that class? Of course, this is kind of a more difficult question, I guess, than the original question, but it certainly implies that question, right? So a positive answer to this question would certainly show us that the algebra A given by the Brauer class alpha is split by a genus 1 curve, namely the genus 1 curve that arises in this particular interpretation. But this is more rigid, slightly more rigid than the original problem, because we're really requiring that the algebra itself, that the curve be embedded in a certain way in a degree n algebra, not just an index n Brauer class. So you have to geometrically, that seems a priori more difficult as a question. But again, it's kind of a motivating question for the approach we're going to take. Okay, so then we're going to implement kind of so-called descent. So this is, again, this kind of technique in the arithmetic of elliptic curves. We're going to implement the so-called descent for mu n isogeny. So here's the setup. So you start with an elliptic curve that admits a so-called mu n isogeny. What is a mu n isogeny? It's just an exact sequence like this of group schemes. So it's a surjective map from E to another elliptic curve whose kernel is the group scheme mu n. Okay, so that's just what a mu n isogeny is. To each mu n isogeny, there's a so-called dual isogeny, okay, where you take Cartier duality and you move some things around, and what you get from that is the dual isogeny looks like this. The quotient is now mapping onto the original curve, and the kernel is actually the constant group Z modulo n. Okay, so to these mu n isogenies, there are these dual isogenies. And combining these two diagrams together, we get this commutative diagram. Okay, that the n torsion, if the curve E admits a mu n isogeny, then its n torsion group scheme is an extension of mu n by a Z mod n, and the extension lives in this nice commutative diagram. Okay. What do we do with that commutative diagram? Well, we just take chromology, and we get, so on here on the level of H1s, here it is, we have, on the level of H1, so this is the, H1 of K with coefficients in Z mod n. This classifies, cyclic extensions of degree n with a choice of generator of our field K. And we get, a map from cyclic extensions to the Weierstrass group of the elliptic curve E, of the dual isogeny elliptic curve E prime. So I'm going to write that as taking a character of the absolute Galois group that determines this cyclic extension. There's a genus 1 curve, C chi, whose Jacobian is E prime, that arises from this theory. And now because of the exactness of this diagram and the equality here, we get that this triangle commutes with these two co-boundary maps, mapping to the H2 of mu n, which is the n torsion in the Brauer group. So we have this co-boundary map, and what does it do? So a standard kind of calculation shows that if you take this co-boundary map and you apply it to the character chi, what you're going to get here is the character, what you're going to get is chi cup the boundary in from degree 0 to degree 1 on the level of the elliptic curve E prime. So that's coming from this boundary map here, where P is that original point, is the generator, right? There's a choice of generator for this Z mod n, this subgroup of order n with a particular choice of generator of n torsion points on our curve E prime. So this is just as kind of a standard calculation, and the calculation then is that this genus 1 curve splits this cut product class in the Brauer group. Okay, so that's the calculation that one has to do. It's a kind of standard chromological calculation. Okay, so we're getting somewhere. And this, of course, this cut product here between a character and a class in H1 mu n, this is just the standard cyclic algebra class, okay, given by that character and that cut product. I mean, plus or minus, or maybe depending on your choice of. Okay, it's the cyclic algebra. So all right, so I just want to point out that kind of from this n descent picture, from the existence, if you have an elliptic curve that admits this mu n isogeny, then from all these sequences in Galois cohomology, you get kind of a natural genus 1 curve, C chi, that splits a cyclic algebra, which is of the form chi cup, and then this co-boundary map, which we don't quite understand. So we get that these genus 1 curves split these cyclic algebras of this particular shape, which we are yet to be determined. So then here's the idea, or the hope at least, that Ben and I had, which is to start with a moduli space of mu n isogenies, of elliptic curves with mu n isogenies, and then take the universal elliptic curve over it, so it comes with a universal mu n isogeny and a universal dual isogeny. So take the elliptic curve of the universal dual isogeny and P, that generator of the n torsion on the curve E prime. So this is like the universal dual isogeny curve with the kind of a universal n torsion generator. And then we compute, this coboundary map. And the hope is that if we take this moduli space somehow sufficiently versal, or this family to be sufficiently nice, that this cyclic algebra that we get is somehow versal, and I put in quotation marks, versal. It's a kind of a versal n cyclic algebra over the field K, kind of as chi varies. So see, your chi can vary over the characters of the n torsion, characters of the function field of the base of the moduli space here. And so as chi varies, the question is, do the cyclic algebras of this form fill up, say, all the cyclic algebras over this, by specializing to points in the moduli space? It's not a true versality statement, because we don't have just like one universal cyclic algebra. We have a kind of a universal element of mu n, of the h1 mu n, and then we have this chi which can kind of range over characters. So okay, it's kind of a versality question. And then the idea would then be, oh well, great, if we do have that, well then by specialization to points in M, if we can specialize to points in M, then we could split all cyclic algebras, because we have universally this genus 1 curve that splits this algebra here. Remember the C chi that splits this algebra here. And if we could just specialize that to points, then we could, and those points we could guarantee that all cyclic algebras over our field K emerge in this way, then we can split all cyclic algebras at least. And ideally, what we could ask for even better is that this class itself, this class, which is a class in h1 mu n, we could ask it to be versal, literally versal for h1 mu n classes. So that would be even better. If it is, then clearly we could get any cyclic algebra that way. So that's the hope, or at least that's the idea. And here's an example of actually that working out. Okay, so the case n equals 3. So this kind of goes back to very explicit work of Kozuma in 2010, who gave, like, here's a nice family of elliptic curves. So here's a Weierstrass equation, which is defined over the function field in one variable. So this is, you could think about this family as a family, a family over P1. P1 is somehow some kind of moduli space of these cyclic, of these these elliptic curves, and each of these elliptic curves has at the origin 0, 0 a 3 torsion point. That is, it's a 3 torsion point uniformly for all the elliptic curves in this family over its function field. So you could think about it as the basis P1, and then the universal curve is given in Weierstrass form by this one. So what then Kozuma actually computes, not for this purpose, but for some descent on elliptic curves purpose, was this first coboundary map associated to this point P here. And what he shows is that it's just literally the class lambda on the nose as an element of H1K lambda mu 3. So that's obviously versal, right? I mean, you can just get any class you want in this chromology group. If you're interested in the class of 7, well then you just specialize lambda equals 7, and then you've arranged that class. So this is obviously a versal class for this over this field. And hence, now we're in a good shape. So we found this class is versal. And so to split a cyclic algebra, if we have some arbitrary cyclic algebra, chi comma a, then we just choose lambda equals a, and then the genus 1 curve C sub chi splits, which is a genus 1 curve, with this Jacobian, splits this class here. Okay, so that's kind of the methodology. Okay, so we just we hope that it works, basically. All right, so let's see how far it can work. So we found in the context of this, explicit descent on elliptic curves business that people have, developed. So Tom Fisher has this method, which in our language computes, here's the input, given a family of elliptic curves over a rational function field with an end torsion point at the origin. So he has, actual computer code to effectuate this, and the Weierstrass form has to be exactly of this form and everything in Tate normal form and whatever it is. But given an elliptic curve over a rational function field with an end torsion point at the origin like that, given in Weierstrass form and actually in Tate normal form, he actually has code to compute a rational function such that the class of this rational function actually computes this first coboundary map associated to this, this universal point over the family. So he actually computes this thing. And so that's what we need. So for example, here's the n=7 case, which is the new case that we were interested in. So if you write down this family of elliptic curves, okay, now don't ask me where we got this family, I'll explain later, but just take it for granted that we cooked up this amazing family of elliptic curves. Okay, so we have this nice family of elliptic curves that has a 7 torsion point at the origin. Then if you run Fisher's code, what you get is that this first this first coboundary map associated to this torsion point P is represented in this H1 Galois cohomology group by just the rational function lambda cubed times lambda minus 1 to the 6th. That's what comes out of it. So what we get is that for any cyclic algebra of the form chi comma this number, lambda cubed lambda minus 1 to the 6th, there is a genus 1 curve, C sub chi, which splits it. But now, it's not totally obvious to me, it wasn't, that like any cyclic algebra over your field is of this form. Like why can we always choose, so there's we have freedom to choose the character as ever we want, because that just takes a different genus 1 curve, and that's fine. So we're free to choose the character, but then why can we choose the class in H1 mu 7 to be precisely of this form? Why do these exactly cyclic algebras of this precise form fill up all the cyclic algebras in the Brauer group? It's not totally clear, actually not clear at all. It's probably not true in general. So then what do we do? Well, we were talking to Saltman actually about this, and he said, oh, well, there's a great trick of Albert that allows you to get around this. And we were amazed by this trick, which we learned from David Saltman. We were really thankful. But so it goes back to some results of Albert, Uzi Vishny, and also Minach Wadworth. So Albert proved this for like n is square free, and then Vishny and Minach Wadworth in general. So the trick, the purely algebraic trick, it just says that if you have a central simple algebra A and it's split by a Kummer extension of the form, nth root of B, well, then it is actually cyclic, and it's cyclic of the form, some chi prime comma B for some chi prime. So the question is then, the idea would then be for n=7. Here's our idea. Take a global field. Take any Brauer class of period 7. So we know that every Brauer class is cyclic. Okay, so we can write it as chi comma A. Then the point is, we use weak approximation to show that we can split that algebra by a Kummer extension of this precise form, taking a 7th root of an element of this form. And that's not hard, because you just have to locally split ramification, and you can do that because you can just, by weak approximation, you can just essentially choose the valuations of these lambdas to have the right shape, and so that's what you do. So you really need somehow weak approximation to know that your algebra is split by some Kummer extension of this precise form for some lambda. So, okay, once you do that, you show that your cyclic algebra, which originally was, given by chi comma a, is actually also equal to chi prime comma this funny expression for some other character chi prime. And then once we have that, then we're in business, because then this we can split by the genus one curve, C sub chi prime that we constructed above. Okay, so you see, that's the game. That's the game. And so where do the modular curves come in? Okay, so what is the modular? What is x1 of n? Well, it is just the moduli space of elliptic curves with an n torsion point p. It's a very classical moduli space. It's actually, one-dimensional. It's a modular curve. Mazur has proved this famous theorem on classifying, say, the torsion of elliptic curves, say, over Q. But part of the output of that theorem shows that this modular curve has, as you range over n, in general, this modular curve gets higher and higher genus and higher gonality, and all these things. I mean, as you range over n, the geometry of this curve gets more complicated. But precisely the cases where this modular curve has genus 0 is precisely in these cases, n is up through 10 and then 12. And in the history, I mean, Kubert may be a bit going back to Tate, which is kind of all around the time of proving this result. They kind of wrote down explicit presentations for the universal curve, which I'm going to write as I did before, this E prime comma P, over the function field of these modular curves, which in these genus 1 cases, I mean, I'm saying in these genus 0 cases, this function field is just a rational function field in one variable. And they, these people wrote down these Weierstrass equations. So the one that we took above, this one in degree 7, this crazy looking thing here, this actually is it's a slight tweaking. We tweaked it for our purposes, but it basically just comes from this classical work of Tate and Kubert. And then, calculations using Fisher's method show that how to compute this first co-boundary map associated to the rational point that you get on this universal curve on the modular curve. And we actually compute them, we actually go through with a computer and compute them in each of these cases. And what we find is that on the nose, like in the case n equals 3 that we already saw, on the nose, these are versal for n up to 5. So actually that gives a new proof. I mean, it was known before, but that gives a new proof that over any field, any cyclic algebra of degree up through 5 is split by a genus 1 curve of this via this construction. And then, if we look at the output, you'll see that for n equals 6, 7, and 10, you get these weird expressions. Like we saw for n equals 7, you get these kind of crazy expressions for this co-boundary map, and then you realize that you can't just use just the straight versality. You need this extra argument, this Albert trick, by splitting by a Kummer extension and using weak approximation. And then furthermore, you find that in like 8, 9, and 12, in those cases, you need additional restrictions, like you need various roots of unity and other kinds of things. So that's somehow where the modular curves come in. And I mean, if you go to our paper, you can see, we have a table in the back of, so here is n. You can forget about this column for a moment. This is just the discriminant of the universal curve in that particular level. But here's the calculation of this co-boundary map associated to P. And you see that for 2, 3, 4, and up through 5, what you're getting is just powers of lambda as this class. And so powers of lambda that are co-prime to n are versal for mu n torsors over the function field k, k adjoin lambda. So that's where you see this versality come in. And you already see, so here's the the n equals 7, and then you see the n equals 6 and n equals 10 have kind of a similar shape. But then in these other cases, there's additional kind of arithmetic that needs to be brought in order to use weak approximation and whatnot. So that is, I think, everything I wanted to say. So thanks.
Thank you very much. Is there any question? Any question? You can also use chat.
Hi, Usher. Can you hear me?
Yes.
Hi. Okay. So thank you for the talk. It was wonderful. Does these exceptions for 8, does this have anything to do with like these Grunwald-Wang exceptions or counterexamples, or is it kind of a different story than that? For like building global extensions with given local data?
Yeah, I think that it actually is. Let me check this quickly. That's my recollection. I'm going to check with you right now and tell you. But that's my recollection was just, well, I don't know if in spirit that's what comes up. But I think what happens is that just given the calculation of this delta, this first coboundary map associated to the choice of rational point, what we get is like lambda plus 1 to the 4th, something like that. And what is the issue? There was some issue with weak approximation there. It might kind of, in spirit have to do with that, but then again, you have the same issue in for 9 and also 12. I think it just has to do with the shape, the precise shape of the actual formula that comes up. That my recollection, I'm trying to read back in our paper, that it just, we were trying to apply weak approximation, and just, there was something where, like, at the real place, because of the shape of the equation, we couldn't guarantee that we could, do things at the real place, or maybe at 2, and at the real place there was some obstruction there. So we had to assume that we could further split that function. But I'm not. I should get back to you. I'll think about whether it has like some deeper meaning in terms of the Grunwald-Wang. I'm not exactly sure.
Thank you. And does it have, are these formulas being complicated related to 8, 9, and 12 having like small prime factors, and somehow the 7 and 10 having big prime factors tamps down the complication relative to the size of n, or is that a misleading way to think about it?
I think that the larger n goes, the more complicated these factors are going to be. Yeah, I think I'm not sure that how much meaning there is to take out of it. I mean, of course, it's also the choice of family that we take. Now, I mean, up to like various, natural transformations, there's really only one universal family over the modular curve. So I think the choice of rational function, I mean, up to nth powers is uniquely determined. But my sense is just that as n grows, then these functions get more complicated. And then also as n gets beyond 12 and the actual base of the moduli space becomes of higher genus, then we just don't have a nice way of writing these, a single family down. And that's the issue. We just don't have like a simple way of writing down the Tate normal form over the function field of the modular curve. That we just don't have, and we don't know how to do. Nobody knows how to do. So
that makes sense.
Asher, just out of curiosity, when the level is 11, what's the genus?
I think it's 1.
Okay.
So yeah, I mean, theoretically, I think it's 1. I'm trying to remember. Yeah, but again, we don't know how to write down. If we had a way of writing down an explicit family that was versal enough of these 11 isogenies, then we could try this approach. You know, even I mean, we're just using one-dimensional rational families, you know, literally over the modular curve, but there might be some like two-dimensional family that is more amenable to, you know, to actually expliciting things. So I just, you know, we don't know. We haven't looked into that. But yeah, 11 is that's clearly the next target for this problem.
No more questions?
So it seems like this method can only be used to split cyclic algebras.
That's correct. That's correct.
So when you said that that gives a new proof for n equals 5, you mean only over a global field?
For cyclic algebras, that's right. That's right. Not in general. I mean, there is. I think I am deeply. I don't know how much I want to say in public, but I am deeply convinced that there is a relationship between this problem and the cyclicity problem in prime degree. I mean, that's my my contention. But and a lot of people are kind of swirling around this connection right now. But yeah, I think trying to prove that every cyclic algebra is split by a genus 1 curve, I think is a very important step in that program.
So it seems like when one works with central simple algebras, somehow the degree is multiplicative, right? Because of the primary decomposition. Whereas you seem to be just working with it additively, you know, from 2 to 3 to 4 to 5 to 6. So 6 should be much easier than 5, for example.
Absolutely. So you would absolutely. So this is where I first got into this. Was I thought, why are we working degree by degree? You know, it should be index by index, or, you know, and yeah, there's a multiplicativity, there's a primary decomposition. So why is 6 hard? I mean, 6 should be easy. If you can split 2 and you can split 3, then you should be able to split 6. But the issue is that any naive way you want to do that, what you need, and this is what I explained back 7 years ago in Banff, is that what you need is to be able to know that, okay, you take a degree 6 algebra and you write it as a quaternion times a cubic algebra. You need to know that you can split the quaternion and the cubic algebra with torsors, genus 1 curves that are torsors for the same elliptic curve. If you can do that, then you can add them in the Weierstrass group and then, you know, use primary decomposition for torsors, and it's no problem. The problem is you just don't know that. That's not a priori totally clear that, you know, that the problems of splitting in degree n and in degree m, if n and m are relatively prime, are kind of sufficiently independent that you can choose a priori which curves. As you see already with this particular, you know, approach, we're kind of forced into, we don't have much choice in the genus 1 curves that we choose. We're kind of forced to use these particular curves that come up in this particular construction as these particular, you know, the maps in chromology. And so the actual curves, if we had a statement like, oh yes, in this degree we can split all algebras with genus 1 curves for any elliptic curve, then yes, we'd be in business. But, you know, actually Saltman has been thinking about this problem, and he found obstructions in degree 3 that you cannot split any degree 3 algebra with a torsor for any given elliptic curve. There are actual Galois theoretic obstructions on the elliptic curve given the algebra. So it makes the primary decomposition for the Brauer group not as useful for this problem, and that's why so far we're stuck to working just degree by degree as we go up, you know, degree 5, degree 6, degree 7, because there's no way to really use the primary decomposition, at least as far as I can see. Does that make sense, Anobi?
Yes, thank you. I have another question. So if you do assume that your algebra is cyclic, how universal is your construction? So if some genus one curve actually splits that algebra, how close can you get to that curve by using this particular embedding into the
Oh, I see.
Brauer severity variety?
I see. You want to go the other. Well, that's a question about the period versus the index of the genus one curve. So basically, what we're proving is that what we're doing in our construction, kind of hidden behind everything, is that we are, I guess, splitting out cyclic algebras of degree n by torsors of period and index n. And so it's possible that you come to me with a cyclic algebra of degree n, and you've been able to split it with a torsor of, period n, but index n squared or something, or index 2n or something. And I don't know if it's then possible to split it with a different torsor where we can reduce the index. I'm not totally clear on. So far, I have to admit, in every construction, so up through 5 in the constructions that we know, and in 6, and now for what we know in 7, we can, given any algebra, we can always split it with a genus 1 curve of period equals index equals n for that index. But we don't know in general whether that's true. That's a further question of merit, And it's known that over an arbitrary field, for torsors for elliptic curves, that the period and index can grow, infinitely far. I mean, there's no like constant period index in general, bound. So yeah, I think that's an interesting question. I think that's a very interesting question.
Thank you.
Any more questions, comments? More questions? If not, then let's thank a speaker for a wonderful presentation. Thank you.
Thank you.